Hi girls, this is a walkthrough of the three problems, the three geometry riders in exercise 14 of your Mind Action series. So the idea, this was a request from one or two students. The idea is that you watch the video going through it, and then during your antimetric math period tomorrow, that's Tuesday, the 31st of March, we can open up a Teams discussion for those who would like to be part and ask questions on it, etc. But I'll try as far as I can in this video to not only just give you the answers, but to explain how you arrive at those answers. Right, so number one, they give us all the information. I'm not going to read all of that. You can read and pause as you wish. But question A is to prove that ABDE is a cyclic quadrilateral. So I'm going to highlight ABDE just for now. So in pink, AB, B to D, D to E, and then back to A. So that's the shape that they're asking you to prove is a cyclic quad. Now remember, to prove something's a cyclic quad, we need either to prove that opposite angles are supplementary, they add up to 180, or an exterior angle adds up to an interior opposite angle, or angles in the same segment, which won't be the case here because we don't have any cross chords, if you know what I mean, to make the butterfly shape. All right, so the first thing I would start with is trying to find angles that are adjacent to the potential cyclic quad and seeing how we can relate those to other angles in the diagram. Okay, what's always useful is to see what other cyclic quads you have. So this is a cyclic quad already. Even though they haven't told us that, we can see it's a cyclic quad because all 4 points are on the circle. So try and make some observations based on the fact that that is a cyclic quad. All right, so based on that, the first observation that I can make is that E1 is equal to C2. And the reason for that is it's an exterior angle of the yellow cyclic quad. Right, so that will be my first thing I'm going to write down. And also, don't worry about writing down things if you don't know where you're going with them yet. It's sometimes, it's fine to write down the information that you've got and then from there make the relationships that you can see. Okay, so that, as I said, the reason is exterior angle of cyclic quad. And then what a good thing to do is, you can see that we've already got a relationship with this E1. So now we know that E1 is equal to C2. Try and find a relationship between C2 and one of the angles either outside or inside the cyclic quad. And here, if you look at the tangent CF or FC and C2, that obviously is equal to angle B1 because of tan chord theorem. All right, so we can say that C2 is equal to angle B1 because of tan chord theorem. And because of this relationship now that we've made here between two different angles, we can conclude that because E1 equals C2 and B1 also equals C2, that must mean that E1 equals B1. And if E1 equals B1, then we've proved it's a cyclic quad. All right, so therefore ABDE is cyclic. And what is the reason? Because the exterior angle, in this case B1, is equal to the interior opposite angle, in this case E1. All right. Right, for question B, they're asking us to prove that D1 is equal to C1 plus C2. Now, the best way to tackle these kinds of questions is they've asked us effectively what is D1. So let's find D1. And using our fantastic mathematical abilities that you have, we can say that D1, we'll highlight D1, and then look what else is D1 equal to. Okay, so you might notice that D1 is an exterior angle of triangle BDC. So the first statement we can make is that D1 is equal to B1 plus C1, exterior angle of triangle. Now, if you look at the information that we need, you can see then that we've almost got it, except that B1 we want to actually equal C2. So the idea is now to go back to the diagram and see what relationship there is between B1 and C2. And in the previous question, we've actually already proven that B1 equals C2. So you can either give the reason again, tan chord theorem, or you can say proven. And that means that we could rewrite this statement as D1 equals, and instead of B1, we're now going to put C2 in plus C1, which is what we are required to prove. Right, for C, proving that FG is parallel to AC, I'm just going to erase all my annotations for this one and highlight for you those two lines. So FG is there and AC is here. All right, so whenever they ask you to prove parallel lines, they always need you to look for alternate angles that are equal, or for corresponding angles that are equal, or for cointerior angles that are supplementary. So we can start by looking at our previous answer. There's a hint there. Okay, but if we look at angle F1, which is over here, and we say, what is that equal to? Now, we know that FG is a tangent, therefore F1 must equal D1, because it's tan chord theorem. All right, so I'm going to write that down as the first step. Remember, again, it doesn't matter if you don't know exactly where you're going. Just try and make relationships between the angles that are adjacent to those parallel lines to start with. Okay, now if we look at D1, we've proven in the previous one, this is why I said your previous answer often helps you, that D1 is equal to angle C2 plus angle C1. That's proven. That means, therefore, F1 is equal to C2 plus C1. Now, what conclusion can we make from that? So if F1 is equal to C1 and C2, then the lines must be parallel because alternate angles are equal. All right, so that's our conclusion. Therefore, FG is parallel to side AC, and the reason is that alternate angles are equal. Okay, in question 2, again, I'm not going to read out the information. I'm sure you've done that already. But you've got to prove that P2, so P2 is over here, that this angle is equal to P4, which is equal to that angle. Okay, so now clearly, let's look at the information we're given. We're given that there's a tangent. We're not given any center of the circle, so we're not going to be using tan radius. We're not going to be using tan from same point because there's only one tangent. There are no cyclic quads, they're only triangles. So effectively, the only rule or theorem that you can use here is tan chord theorem. So the idea is to try and, again, make relationships. So the first thing we can say is that P1 and 2, and it doesn't matter if you started at P4 and 5, that's also fine. But P1 and P2 must be equal to C1, all right, if we're looking at this triangle. Okay, so P1 and P2 is the angle between the tangent and the chord BP, which then is equal to angle C1 on the opposite side of the triangle. Okay, so let's write that down. So P1, not equals, but plus P2 must equal C1. That's tan chord theorem. And the next thing we can say is let's make another relationship between angle P and something else in the triangle. So if we look at C1, D, angle D plus P4 must equal C1, and that's exterior angle of triangle. Okay, so I'll show you that now. So we're saying that C1, this one, is equal to angle D plus P4. So you see what I've done here? They want P2 and P4. So I've specifically made equations that deal with P2 and that deal with P4. Now we already have that they're both equal to C1. So we can then make the conclusion that must mean that P1 plus P2 equals D plus P4. Okay, so at this point, we have this equation, which is longer than what we needed. But you notice that there's a P2 on the left, there's a P4 on the right, but we also have a P1 and we have a D. We need to get rid of both the P1 and the D. So, looking back at the diagram, look where P1 is. P1 is there, and D is here. But hang on, there's a triangle here. And P1, therefore, must be equal to D because of tan chord theorem. Okay, so we're going to make that statement, but P1 equals D, and the reason is tan chord theorem. And that means if P1 is equal to D, we could effectively replace the P1 here with D, and then we'd have D there, we'd have D there, and we could then cancel them. So then we'd left just with, therefore, P2 equals P4. Right, in this one, they are asking us to prove that DE, so this line, is equal to EC, that line. Now, the moment they ever ask you to prove two sides are equal to each other, it's almost always isosceles triangle that's involved somehow. So you have to basically we need to prove that this angle, C, is equal to D1 plus D2. So if you would like to, you can even write that down, that you are required to prove that angle C is equal to angle D1 plus D2. Then that helps you with where you're going with the problem. All right, so let's look at what they've given us. We know that there's a center of the circle. There are no tangents, though, so we're not using tan chord theorem. We're not using tan radius. There are also no cyclic quadrilateral, so all of those theorems are out. There's no lines from the center to the chord, to any chord, so we're not going to be using any of those theorems. So in fact, here, there are actually no circular theorems that you can possibly use in this diagram except for angle at center. All right, so straight away, if you look at O1, we can tell that O1 is double OC because of angle at center. We'll get to that. But the idea now is to try and work out those angles C and D. So try and make relationships with what you have. So straight off the bat, we can say that angle E1 is equal to angle C plus D1 plus D2. And that's exterior angle of triangle. All right, so now your problem is we've got the C, we've got the D1, we've got the D2. We've effectively got to get rid of that E1 somehow, because then we would have almost all the angles that we need in the equation. So another observation, as I said earlier, is that we can say that E1, remember we're trying to get rid of E1, so we have to find other angles that are equal to E1, must be equal to O1. Okay, so what I've said is that E1 here is equal to that O1 because there are angles in the same segment that are subtended by arc BD in the small circle. All right, so the reason for that is angles in the same segment. But now angle O1 is one that we don't want in the equation either. So what relationship can you make with angle O1 to any other angle in the circle? All right, and we can clearly see that angle O1 is equal to twice angle C, all right, and that's angle at center theorem. All right, so if angle O1 is equal to E1, as we've said here, and angle O1 is also equal to 2C, then that follows that angle E1 equals 2C. So we can replace this 2C back into this equation. Okay, so that would give us 2C equals angle C plus D1 plus D2. And now we just use a little simple algebraic manipulation. We can take that C over to the left-hand side, subtract it from 2C. To get 2C minus C is positive C, which equals D1 plus D2. And that's now what we were required to prove. So remember right at the beginning, what did this mean if we could prove that? It would mean that this angle over here, C, is equal to D1 plus D2. And now that we've proven that, we can therefore conclude, therefore, DE equals EC, and the reason is isosceles triangle.